we're going to discuss, explain the DeMoivers theorem in this topic and this video. Now, the DeMoivers theorem is a theorem that used to find the power of complex numbers, okay, or evaluate complex numbers inside powers. So, for example, we use in the DeMoivers theorem, mainly we are using the polar form. So you'll have, even if the question is in the rectangular form, you'll have to convert it into polar form first. And then and the rules is z to the power of n. So if you have a complex number all to the power of n, you can evaluate that, and instead of expanding, which could take quite long, if you have the power of 3, 4, or even 10, you find the modular, you evaluate the modular, because modular is just a number, so it will be to the power of, evaluate that to that power, and then you multiply the theta or the argument by the power. So for example, and then you can convert the result back into rectangular form. Now, for example, we've got this one here, that's it. In the previous, we could do, for example, if you have z squared, you can expand it normally. Okay, that's easy, straightforward. If you have z to the power of 3, for example, you can still expand it, but it takes longer, and there is a very high possibility that you make mistakes when you are multiplying the i's. Could be, mostly it will be a sign mistakes, negative and positives. And then expand, simplify. That takes time and could be effort. Makes mistakes, possibility of mistakes. But if you use the DeMoivers theorem, it's way more efficient and it is way less to make mistakes. So for example, you can convert your complex number in the rectangular form, you must first convert it into polar form. Then you can apply the rule. So if you want z squared, you're only going to square the modular will be 4, and then you multiply the argument by the power. And that's the answer. Z to the power of 3. Just take the power of the modular and then multiply by the. So now if you get the z to the power of 3, you can see it's quite easier to calculate the answer. Just multiply the 3 by the angle as well. So it's way more efficient. Now, give your answers in a polar form. So that means you just leave the answer in the polar form. You don't have to convert it back into rectangular. So all to the power of 6 means 3 to the power of 6, and then multiply the 6 by negative 120. And then that's your answer for the using the DeMoivers theorem. The next one, all to the power of 9. So multiply, take the square root of 4 all to the power of 9, and then 9 times pi over 4. Now, you can leave your answers in negative powers, or you can leave it at 9 pi over 4, but it's better to get the actual theta. So remember, this is 9 pi over 4, so it will do 360. So it's 2 pi minus pi over 4, give me pi over 4. Or, 9 pi over 4, give me pi over 4. Or you can do, in here as well, it's 360 minus 720. That 720 is double 360, so that's y is 0. The angle is 0. So you do anyway. So the final answer, you will do 360 minus, just to get the real theta, the actual argument. So in here you've got it in the rectangular form. So you need to give your answer back into rectangular form. So the first step is you convert this rectangular form into polar form, as we've explained in the previous video, by finding the modular and the argument. Now, by finding the modular and the argument, you will get this cis, and then you will apply. So the polar form for this one here is 1 cis negative 45, and then you will get all to the power of 5. You apply the DeMoivers theorem. Now once you get to this answer here, then you will have to rewrite it back into the rectangular form by using cosine negative 225 plus I sine 225. Or you could do cis first, convert it into the real argument, which is 360 minus 225, give me 135, and then you will do the cosine for 135 plus 1 sine 135. Either you do this step here, the 135, or you can do it straight away from negative 225, give me the same answer. So whatever, if you remember to that step, the answers are smaller, but if not, then you'll just get the same answer anyway. Alright. So we've got z plus 1 over cosine. This question here is prove. So you need to prove that z plus 1 over z equal to cosine theta. To do this one here, that you will have to use your trig, for your trig identities. Now we haven't done the trig identities yet, but you can always view it on your formula sheet. There is a bunch of identities that you can use. Otherwise, you can always, to prove any proving identities or proving any statements, is actually working on the left hand, choose one side to work on. Because the 2 cosine theta, you cannot expand it anymore, so that's, leave that side. Then you start with z plus 1 over sine. Because you want the answer as a cosine, so obviously you will have to write the z using the polar form, which is the cosine theta plus I sine theta. So the left hand side we start with, so you rewrite the z that way here, okay, and then you will find the common. So because you've got, can you see that denominator here has the complex number? Remember, when we do complex numbers at the denominator, we will multiply by the conjugate of the denominator, so we can end up with a whole number in the denominator, but after simplifying. So that's what we're going to do now. So we multiply only that fraction by the conjugate of the denominator to simplify. Now cosine square theta plus sine square theta, this is one of the identities that I was talking about, which is give me equivalent that's equal to 1. Identities are facts, so you use them as they are. So cosine theta plus sine square theta is equal to 1. So that's 1. Now you've got this, now collecting the like terms, so you've got cosine theta plus cosine theta, that give me 2 cosine theta, plus I sine theta minus I sine theta will eliminate, and that's what you get there, right hand side, so it's proven. Now we'll do the next question. So the next question is again another proof, so it's kind of similar, but this time obviously we will have to use the DeMoivers theorem because we've got square in here. So we're going to write the z first as a cosine and sine, the polar form, and then we use the DeMoivers theorem as expand, probably expanding here is easier. Yeah, so we'll expand and then simplify. Yeah, so we'll expand and simplify. Now just multiplying by the denominator, so it's all the same steps as before. Now once you've divided, so remember the cosine square plus sine square, it's equal to 1. So that's why this gives me 1 square. This one here is just basically that's times 1, so that's why you end up with this. So now you've got that plus that, so you will have to expand now. After you've expanding everything, we'll simplify, adding the like terms. That will simplify, and then you will end up with 2 cosine square theta minus 2 sine square theta. Now, this is also another trig identities that you will be using. 2 cosine theta minus sine square theta, taking the 2 as a common factor. Now, cosine square theta minus 2 sine square theta, there is a trig identity with the square of cosine, and that's those two give me the cosine 2 theta. So this is a trig identity that's equivalent to cosine 2 theta. Okay, you can always see those trig identities in your formula sheet, but I will do some tutorials, go through them because we'll need them a lot when we go to integration. Thank you.